Today what we're going to look at is more stuff on the normal distribution. And what we're going to do this time, well, I have a little sketch here. I'm just going to outline the sort of stuff what we're going to do. If you know the mean and you know the deviation, you've got this kind of a bell curve or normal distribution. What if you knew precisely what proportion or probability you were interested in? So this here was known. So we might say that represents 10% or something like that. And you wanted to know, well, what number here, what was that number there that corresponded to this particular percentage? That's the kind of stuff we're going to look at today. How do we find these numbers here? Now, I think this is going to make itself a lot more clear when we do an actual numerical example. So that's what I'm going to do. So let's get a little board space here, and we're going to go to an example involving cherries. And what we're going to say is that for cherries, if we say got a nice big sample, we were able to say the mean weight of a cherry was 7.0 grams. And we might say, well, from our sample we got a standard deviation of 1.1 gram. Now, we might be interested in a question something like this. We might want to find the sizes of cherries that contain 90% of cherries. So let me draw a little picture, and I really recommend that. When you're working with any kind of distribution, especially some of these more complicated problems, you will find if you draw it out, it makes it very clear what kind of zones you're after. Which areas of the graph are you trying to figure out? And so that really, I find, is a very good strategy. So let me just draw what our distribution might look like. We're told, presumably, that cherries are normally distributed. So we've got our mean here in the middle of 7.0, and we've got a certain deviation. What we're looking for is from what size smaller than 7, so we're going to call that maybe A, from this size to what size over here, which I'll call B. So these are the two numbers we're trying to figure out. One smaller than the mean, smaller than 7, one larger than 7. And we want to figure out what these numbers are such that this area here corresponds to 90%. So in other words, this whole zone here has to be 0.90. So how do we find these numbers here? Well, the first thing we're going to do is we're going to change the parameters here. Yes, that's 90%, but what that also means is that this little wing on the left and this little wing on the right have to add up to the remaining 10%. In other words, this little wing here is 5% or 0.05, and so is this one over here. Remember that under any kind of a distribution, probability distribution, all of this area has to add up to make 1. And so we're using that strategy and saying, well, 0.9 is represented in the middle, so we need 0.05, 0.05. So what we're now looking for is what number, if we start with A, corresponds to 0.05 being the area on this left wing. And that kind of question can easily be solved. There's a command on most calculators, and especially the one I'm using is the TI-83. The command would be found under second function, vars. So you access the distributions and you pull up this one, inverse normal. What this does is it answers precisely the question that we're after here. We know the mean, we know the deviation, and we know what probability, cumulative from the left, we would like to have in this little wing. Remember, these probabilities are always cumulative from the left. So to find A, we would put in the following: 0.05, comma, 7, our mean, and then our deviation of 1.1. And we'd hit enter, and we would get this number here, 5.19. So that's what A is. All right, so that's our first number, 5.19 grams. That's kind of the low end of the spectrum, the low end of our 90%. Now there's a couple different ways that we could proceed to finding B. Probably the easiest way, there's a little bit of room here, the easiest way to do this, and there's a really nifty little way to duplicate this whole command without having to retype it all in. And that is, you go second function, and then you hit enter. What that will produce for you is precisely the previous string of commands. So you have all this stuff here, and then you say, well, actually, I just want to overtype one thing. I'm going to use inverse normal again, but this time to get B, cumulative from the left, the total area under the graph would be 0.95. The reason being is you want to include the 0.9 and the 0.05. All of the stuff from B to the left. So we would just overtype this, and we'd still have this left in there from before, and we'd hit enter, and we'd get the answer of 8.81. So what our answer would be is, to encase 90% of cherries, we would go from 5.19 grams all the way up to 8.81 grams. It's the easiest way to do it. You could have used symmetry. This distance from 7 down to 5.19 is precisely the same distance up to B. So what we could have done was taken 7 minus 5.19. So we could have done this and found the difference between them. What's that going to be? It's going to be 1.81, it looks like. Then I would have taken this number and added it to 7, simply recognizing that that's the distance I want to go either side of the mean. Certainly could have been another way we could have done it. Okay, so that's that example worked. Now I'm also going to show you one other strategy that can be useful on other kinds of questions. So this is the same question, but with a slightly different method. So I'm going to clear this away. We now know what the answers are, and we did that rather nicely using the calculator. That would be my preferred way of doing it. Let me show you another little method. So I'm going to leave kind of my drawing up here and work from it. So no calculator commands now. How do we do it? Well, what we would do, there are these pages called the Z-score tables. And what that does for us, and you'll find these in the textbook that you're using. You'll find them in any stats book. They'll always have Z-score tables. And the way that works is as follows. I'll just sort of give you an idea over here. You look for the Z-score, the area under the graph that you're interested in. For example, 0.05. So somewhere in here, they've got all these tons and tons of numbers, and you try to find 0.05 or something really close to that. So say we found this guy here. Then we look at cross-referencing which row and which column corresponds to 0.05. What they will do is they'll give you one decimal place here, and then the second decimal place here. So you put the two of them together, and that's how you can find out the Z-score. Now, I like to do that electronically, and so if you wanted to find out what this Z-score was that corresponded to 0.05, and maybe I'll just show you exactly what we're talking about here with a handy-dandy graph. If we took our bell curve, the same information here, and we decided to put it on the standard normal distribution, where we have a mean of 0 and a deviation of 1. Every time we find these numbers A and B, they get worked into what are called the z-scores, which are the numbers along the x-axis. And so, this number A, I would simply find out what the z-score is for A, and the way I would work from the table is by looking up this 5%, or 0.05. Now, there's a way you can do it directly on the calculator, and again, what you would do is inverse normal, and you would put in, oops, better turn it on, inverse normal, and we'd put in 0.05. Now, by default, the machine will use a mean of 0 and a deviation of 1. You don't have to type it in, because that's what it'll do by default. And, all right, that's a little bit strange moving here. All right, got too many commands going on at the same time. I'm going to try that one again. And inverse normal 0.05. All right, there we go. Finally got it working. So the z-score we would have looked up is negative 1.6. This one would be to 0.64. Now, what that means is if you were using the actual z-score tables, if you looked up 0.05, you would have had negative 1.6 along the row, and along this column you would have got the 0.04. So you basically put the two things together to get your z-score. But a faster way to look up your z-score is simply to throw inverse normal and whatever percentage you want into your calculator. It looks it up a little quicker for you. Now, if you look up this z-score, it's probably a wise idea to look up the other z-score. So I'm now going to go inverse normal of 0.95. Now, because it's symmetrical, I could save myself that bit of work and predict that this one across here is going to be positive 1.64. And I think we'd be just fine in doing that. But sometimes you like to double check. Doesn't hurt. So we did get positive 1.64. Now, what we're now going to do with our z-scores is the following. So I'm just going to get rid of this. It has served us well, but I need the space. What I'm now going to do is go to our formula, which looks like this. You take whatever x is, or in our case we called it a, whatever that actual number is, minus the mean, divided by the deviation, and that equals the appropriate z-score. So now I say, well, I know what the z-score is. It's negative 1.64. And I'm looking for x, which we were calling a. So I'm going to replace it with a. The mean is 7, and the deviation was 1.1. All I have to do now is go ahead and solve this thing and see what I get. Well, I would multiply by 1.1. So I'm going to go 1.1 times negative 1.64. And to get a, I would then add 7 to this number. So I'm going to take this number here and add 7 to it. Well, let's go ahead and do that on the calculator. Actually, I'll just write the whole thing out here. So we got this plus 7. Actually, I know the answer because I wrote it down already. 5.19. Well, hey, isn't that what we got before? This is just a different way to do it. And sometimes knowing this formula and using this formula is really, really important because we can't always rely on the calculator method. It's a good method, but sometimes it doesn't work in all problems. So you got to know how to do this. Of course, now you can use any method you want to get the other one. I could use precisely the same build-up. The only difference here is that we'd be looking for B, and the difference over here is that this would be positive 1.64. So we'd go through all this stuff here, be identically the same, pretty much, except for B and the change in this being positive. And guess what? We get 8.81. So you're going to get the same answers, but it's just a different way of doing it. And as I stress, you have to know how to do it both ways. Okay, I think with that, we're going to stop. This is basically our complete look at the normal distribution.